think we're live. Yes, we are. Wonderful. Welcome back, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going to be your host. Today, we are presenting Proving Fundamental Physics with Heavy Radioactive Molecules by Ronald Fernando Garcia Ruiz. Ronald is currently an associate professor at the Department of Physics at MIT, and his research is focused on the development of laser spectroscopy techniques to investigate the properties of subatomic particles using atoms and molecules made up of short-lived radioactive nuclei. He obtained his bachelor's degree from Universidad Nacional de Colombia in 2009, and actually that was the year I joined Universidad Nacional de Colombia. And then he got a master's degree in La UNAM in 2011, Universidad Nacional Autónoma de México. And then he moved to Europe, to Belgium, to start his PhD at KU Leuven. And then he was there, and most of his PhD was actually at CERN, with an intern at the University of Manchester between 2016 and 2017 as a research associate. And then he joined the MIT physics department in 2020. So we are very happy to have you here. And today he's going to tell us about how these molecules are emerging as a powerful new frontier in the search for new physics. So for everyone, remember that you can ask questions over email or through our YouTube channel, and the questions will be read at the end of the talk. So without further ado, we'll turn in time to Ronald. Thank you, Ronald, for joining us, and thank you, everyone.
Good, yeah, thank you very much for the introduction. So let me share my screens. And yeah, thank you for the invitation.
Perfect.
So it's a pleasure to share with you some of the work that we have been doing. So this is a cartoon of the experiments that we do, okay? So in our lab, we try to mix or to create a soup of visible matter that we can control, hopefully at the most fundamental level. Okay, we know we can have electrons, neutrons, and protons. We cannot control individual quarks, right? That's what nature allows us to have these neutron, protons, and electrons that we can use to create particular atoms or molecules. And the idea is that there are many nuclei that they might not be available in our planet, but they can be created artificially. And this imbalance between protons and neutrons is going to help us to investigate a particular phenomenon. And our group does this to investigate very different phenomena, but in this presentation, I'm going to focus in high energy physics. That is one of the main focus of these seminars. So what's the idea? So before I go into the details, I have to say that these are relatively small scale experiments. Okay, we're about few PhDs. We still call tabletop experiments. And this is our group, which I have to recognize they have been doing most of the job of being able to create those atoms and molecules and doing the experiments that I'm going to present. And we don't do this alone. So this is part of a collaboration. And again, those collaborations are not so large, about 2-3 PIs. So this gives you a scale of this experimental work. So each experiment will be 2-3 PIs from different institutions, or in some cases a few more, and a few grad students and postdocs. So the job of each grad student is really instrumental for all that we are going to present. And we don't do only, this is not possible only with experiment, but theory plays a very important role. And that's one of the parts I like very much, is that this is a truly interdisciplinary work. So we want to answer questions of nuclear and particle physics, but the technology that we use is mainly atomic and molecular physics. And we need theory to motivate the experiments, to help us to design the experiments, and to make the interpretation of what we see in our experiments. So let me start with a sentence that is quite intriguing for me, and that comes from Michelson in 1894. And he has this famous sentence that sometimes is misleading for if you only read the few sentences, and is that he said that at that time, 1894, that the most important fundamental laws and facts of physics have all been discovered. Okay, that's 1894. No quantum mechanics, no relativity. We didn't even know about the electron, no nuclear physics, no the modern physics that we know today, right? And he basically suggests that so all is so established that the possibility of something new, the new discoveries, is becoming very remote. Okay. And for me, it's very exciting to think about that moment, right? How physicists might have thought that all physics was discovered. But Michelson, he was a very clever guy. So he basically, if you continue reading this letter that he wrote in Chicago in 1984, he later said, nevertheless, it has been found that there are apparent exceptions to most of the laws. And he basically pointed to the fact that we need to look into the high precision experiments. That even though we think that the laws are well established, when you start doing precision experiments, in that case, at the sixth place of decimals, people start to see deviations of what we thought were well-established facts. And he described two examples. And one was the famous experiments of that you measure very precisely the orbits of Uranus, and it deviates with the theory. Okay. And that's an example where you have precise theoretical predictions, you do a precise experiment, and they didn't match. And the solution was that there has to be something new, a new planet, and that was the discovery of Neptune. And that perhaps gave origin to precision astronomy, right? So we start to think about doing a precise theory a calculation with a precise experiment to discover something new. And also he gave the example of the weight of different chemical elements, and there was something missing, and that gave the discovery of argon. So those are very beautiful experiments, how you identify precision as your tool for discovery. And nowadays we have other problems, right? So we are not looking only into one planet's deviation, but we have big problems, right? And I don't need to motivate this for this audience, but we know that there is something out there that we call dark matter and dark energy. And we know that our most fundamental model, the standard model, gives a very good description of nature, but it's incomplete. So it's missing important aspects of our universe. So they are still, and we know there are important open questions. Now, how we investigate some of those questions? So one very successful approach is to do collider physics. Okay, so imagine you want to investigate what's happening or how the nucleons interact, or the interactions between fundamental particles at the subatomic level. One approach is to send a high energy particle. I just given the example of the electron because in the US we are building an electron ion collider. And then the higher the energy of my electron, the deeper I can prove the inside of the distribution. So what we do is quite different. So we don't accelerate the particles, okay? Instead, we leave the nucleus untouched, and we put electrons around the nucleus. Basically, we form an atom. And now the atom, the electron in the atom, has a wave function, right? And for example, an s orbit, in the case of radium, has the electron wave function has an overlap with the inside of the nucleus. Although the electron is most of the time outside my nucleus, there is a small overlap of the electron wave function with the nucleus. So if I measure very precisely the electron, then I can learn something about the interactions that are happening within the nucleus. And that's basically the approach that we do in our experiments. Instead of sending a high energy particle, I rather do a low energy experiment where I can measure very precisely the energy of this electron. Now, the problem with atoms, or the challenge with atoms, is that the orbit that has the best overlap with the nucleus, the s orbit, has spherical symmetry. So although the electron might have an overlap with the nucleus, the spherical symmetry prevents me to learn much of what's happening inside the nucleus. And that approach that was a main motivation for me. That might be obvious for many of you, but for me, that was something that I learned not long ago. That you can take an orbit like in an atom with that s orbit, and you can put another atom next to it and form a molecule like fluor. And fluor likes to be negative, so now what it's going to do is going to push the electronic cloud, and they form a molecule that now has a sigma orbit that is very much like a deformed s orbit. So now the initial s orbit in the atom is deformed such that the electron still keeps a good overlap with the nucleus, but I broke spherical symmetry. Now I can ask my electron, by measuring the electron energy levels, I can be sensitive to this part of the wave function when they overlap with the nucleus. And that gives me access to very different physics. Okay, now I can be sensitive to the electron-nucleon interaction within the nucleus. I can be sensitive to the weak interaction. And with my lasers, I can change the spin of the electron, and I can change the spin of the nucleus. I can do very well controlled and precise experiments. I like to say this looks very much like electron scattering at very low momentum transfer. Okay, the molecule is my accelerator that is sending the electron back and forward into the nucleus. And that has been what we have been trying to do in the last few years. So let me put some scales of the energies that we are speaking about. So you take two atoms, you put them together, so you form a molecule. In this case, a diatomic molecule, a simple molecule. And the energy levels are typically in the electron volt scale, the electronic energy levels, line atoms. Now, the molecule can vibrate, and these vibrations are at the scales of typically 10 to the minus 2 electron volts. But the molecule can also rotate, and rotations are typically 10 to the minus 5 electron volts. And now, if I go beyond, I start to play the game that I like to play as a nuclear physicist. This is where our main work goes. If I go beyond, now this overlap of the electron wave function is going to produce effective fields at the nucleus. And now the nuclear properties, the nuclear electromagnetic moments will interact with those effective fields. That's basically the hyperfine structure that we have seen in atoms, right? And give me access to all of these nuclear properties. And if I go beyond, now I need to include the effect of the weak interaction. And now the WC exchange between our nucleons are going to contribute to the electron-nucleon interaction. This is typically at the 10 to the minus 12 electron volts for these particular molecules. And I can go even beyond. If the quarks are not point-like, or if the electron is not point-like, they have like dipoles. So I can be sensitive to these permanent dipole moments, either of my electron or the nucleon or the nucleus as a complete quantum system. And those dipole moments are very exciting because they are related to major open questions in our understanding of the universe. And you might have seen that before, but the existence of a permanent electric dipole moment will imply the violation of both parity and time-reversal-symmetry. And I don't need to motivate this for this audience, but time-reversal-symmetry is equivalent to the combined charge and parity violation. And CP violation is one of the main motivations. So look for new sources of CP violation is a main motivation, not only for our experiments, but many experiments in collider physics and in particle physics and neutrino physics. And why is that? Because for questions like the very origin of matter in the universe, we do not understand why, after the Big Bang, matter was created in a larger amount compared with antimatter. We don't know the origin of this matter-antimatter asymmetry. And one of the conditions to explain that phenomena is the need of CP violation beyond our current observations. Now, we have seen CP violation only in the weak interaction, but in our standard model is parameterized as theta, and we don't know why we haven't seen that, right? Although it's there, it's allowed in the standard model, in the strong force, we haven't seen that yet. Or this parameter is unnaturally very small. So that's known as the strong CP problem. And a way to explain that problem, so some colleagues here at MIT, so Fran Wilczek proposed, and others, that there might be some dark or some particles that can be dark matter candidates, actions that will explain why this is too small. And of course, I just said, these are candidates for dark matter. So bottom line, what we can measure in principle at the lab are these dipole moments of my nuclear distribution. And as an experimentalist, I'm very excited that this can help us to provide answers to very important questions in our understanding of the universe. Now, how we do that, right? You have a dipole. It can be a dipole of the nucleus, the electron, or the nucleon. So the simplest way to measure this dipole then is apply an electric field. Because if I apply electric fields, external effective fields, now you know this very well from electrodynamics or, well, electrostatic, that now the interaction is going to be a product between the nuclear moments or the moments of this charge distribution with the different magnetic fields or field gradients or so on. And typically in AMO classes or in electrostatics, you don't care about this dipole and the magnetic quadrupole, because you say this violates parity. So you don't take that into account. But that's the important part for us. So this dipole interaction with this effective field is what we are trying to measure. Now, if the dipole is very small, as we know it is, because we know CP violation, we don't know many sources of CP violation. We know that that's very small. You would like to have the largest possible effective field. Okay, that's the end of the game. How we can produce these effective fields. And for us, the atom and the molecule are these external electric and magnetic fields. So that's what we do. We create this nuclei, we place in the right molecule, and then you can access to gigantic fields of the order of gigavolts per centimeter for some particular molecules. Just to put the scale, the best that you can do at the lab is about hundreds of kilovolts per centimeter. So these molecules, if you produce the right molecule, you can reach gigavolts per centimeter, many orders of magnitude larger than you will be able to do at the lab. Okay, and that's the key part of the molecule. So experimentally, we create this molecule, this single molecule or atom, and then we measure some energy levels. Okay, that's all that we want to do. And what we see in our experiments is a peak. Okay, we can, for example, scan our lasers, and when the lasers are on resonance with a particular transition, we see a peak on this particular energy level. So let me close the door just. So we see a peak in our experiments. So that's experiment one. And now we can, for example, polarize the molecule. And now there will be an effective field in one of the levels that is proportional to this dipole moment, can be the electron or the nucleus, as I said, with effective field within the molecule. So now the peak that I see before is going to shift. And what we do experimentally is to measure the level, this energy difference directly. So that's very different. We don't want, and that's very important because it's confusing for some people that see our experiments. We don't want to measure 10 to the minus 12 or 10 to the minus 18 term on the top of something very big. Okay, although it's possible, we have seen atomic clocks that are already at that level, But that's not what we want to do in the experiment, because we basically build a molecule, it's a Hamiltonian, that is insensitive to this particular dipole, no effective field. Now we apply the effective field, and such that all of these terms remain constant or well controlled, and then we take the difference. So when we take this difference, we don't care about all of these big terms that appear in my energy levels. So all of them are removed. So I can measure directly the contribution from my time effect that I'm going to look for. Okay, that's very different than measure an absolute value when I take the relative values. So then experimentally, what's the idea? So this shift to be able to see in the experiment depends at least on two factors. My nuclear shape, my nuclear parameter, my nuclear dipole, the effective field within the molecule that this nucleus experience, and this is going to give me the separation between those two peaks, okay? But experimentally, I depend on how precise I can measure these two peaks. And that's going to depend on the statistics, that's my n. And it's also going to depend on my coherence time, because the more that I measure, the smaller is going to be this line width. So then the experiment I want to do is to create artificially the nuclei that maximize the blue part, then be able to interrogate my system for the longest possible time. So you would like a trap experiment, and you would like to increase the statistics. So measure many times and hopefully have many molecules together that you can increase your number of measurements. So that's basically the principles of our work. Conceptually, it's very simple, and indeed, experimentally, this has been done for two particular molecules, well, several, but there are two recent results. That's not from our group, that's from our friends. So they have been using thorium oxide and cadmium fluoride to measure this property of the electron, okay, the electrostatic dipole moment. So nowadays, the molecules took over this field. So when we plot how well is the constraint of this moment, so those are units of, because traditionally people use electron multiplied by centimeter, but what you can see is during the years at the beginning, or well, around 2000, the best experiments were done with atoms. Around 2011, molecules took over this field, and they have been improving these constraints of this dipole moment. And improving means, and in this case, I present in different extensions of the standard model. So in this case means ruling out different extensions of the standard model that predict these new sources of CP violation. And important here is that there is a lot of room for improvement. So nowadays, the molecules are the best system to prove this fundamental property of the electron, okay? There are no other systems that can do that for these properties that I introduced before. Now, this might not tell you much, this number. So in the community, you can relate the existence of a dipole with the existence of a new heavy particle, okay, an unseen particle. You can imagine you don't have a dipole, but once you have a new heavy particle, it can induce this dipole moment, this CP violation. And then you can associate, or you can relate the magnitude of the dipole moment with the mass of this new heavy particle. And to put some scale, so with this naive one loop, assuming a maximum CP violating phase that we have to assume, and order of this one of the coupling constant that we know, just to give an energy scale. So you will realize that those experiments are already proving the TeV scale. Okay, constraint in these electron EDMs will be equivalent to constraining the existence of this new heavy particle at the TeV scale, which is very powerful, okay? Because now it's on a scale that is interesting because it's at the scale of the Large Hadron Collider. So now we don't want to measure the electron EDM, so we would like to measure the equivalent, but the nuclear EDM. And what's the reason? The main reason is the electron EDM is whatever nature give us, okay? We cannot do much. We cannot modify the electron EDM. But for the nuclear EDM, we have a lot of freedom to modify the nuclear EDM because the collective nuclear EDM is going to depend on different parameters, on the total of nucleons, the atomic number, and the quadrupole and octuple deformation. So, and also the energy difference between states of different parity. So then at the nuclear level. And it turns out that in nature, most of the systems minimize this octuple deformation. Octuple is like this avocado shape of the nucleus. So most of the nuclei don't prefer to have this shape. Or say the other words, when you try to create these octuple deformed shapes, these avocado shapes, by changing the number of the imbalance between neutrons and protons, the nuclei became unstable. Okay, this is an unstable form of nature. And it was discovered some years ago that there are some particular nuclei that at least keep this shape for some time. In this case, 2 weeks, about 2 weeks, and that's radium-225. And this optical deformation, then you can see in the following way. So let me summarize. You have some CP violation at the fundamental level. So maybe the quarks are no point-like. They have these dipole-like structures, or the nucleons or the protons. You put all of this together in a nucleus, then maximize that by a factor of more than 10 to the 3 respect to stable systems. And now when you have this enhanced nuclear EDM, you can place that within a molecule. And this EDM is going to interact with the effective field of the molecule that can be, again, be amplified by more than 10 to the 3 respect to atoms. So you end with an amplification that can be more than 10 to the 6 respect to an atom with unstable nuclei. And that's a huge number, right? An amplification of more than 10 to the 6, but it doesn't mean much if I don't put in context. This plot is just to highlight that this optical deformation happens. Quadruple deformation is very common in the nuclear char, but optical deformation only happens in some specific regions, and all of them are radioactive. So now, what can we say with this 10 to the 6 enhancement, right? 10 to the 6 is a huge number, and that's exciting, but we can put this number in terms of an energy scale, okay? Like constraining the equivalent nuclear EDM, as we did with the electron, we can associate a mass scale of the particle that we can prove. And this plot is trying to show that that's the mass scale of a possible new particle. These colors are the different EDMs. So people have been doing those experiments with the neutron EDM and atom EDM. And this optical deformation of nuclei was recognized a long time ago, and people have tried to do it successfully with atoms. And this bar is the direct constraints, right? So we know at the LHC, we haven't seen new particles at the TeV scale. On the other hand, at the upper side, we have another limit, or at least we know that we have seen some CP violation. Okay, there is some CP violation in the CKN matrix elements, right? So we know that there is a limit where we start to see something. So the idea is that we hope there will be some CP violation in between. That's what we call the windows of discovery. So any new source of CP violation, we expect to appear in between our current limit and what we know we have seen already. Now, to put in that scale, the molecules that we are using, even with a single molecule, this 10 to the 6 enhancement tell us that a single molecule in a very short coherence time, about 100 milliseconds, in 2 weeks, you will be able to be very competitive with the state of the art. And that was a main motivation to do this kind of experiment. If we manage to trap a single molecule, we will be able to go to the state of the art, constraining this CP violation. And once you are there, it's exciting because you can start scaling the experiment. You can always put more and more molecules and interrogate for longer and longer times. And you can put numbers that sounds very optimistic, but becoming real and fully cover these windows of discovery. And that was very exciting for our community, that you have a system that will allow you to prove this high energy scale, okay, of the order of 10 to the 3 TeV. So that was the main motivation to do those experiments. And we have to start from the very beginning. So many of those nuclei are poorly known. Certainly the molecules were unknown. There is very little knowledge about radioactive molecules. And definitely there was no spectroscopy, high precision spectroscopy of those, not even low precision for this particular molecule, radium fluor. That was our first experiment that we wanted to do, or we came with this idea in 2019, 2020. And that was our dream when I joined MIT, that was about this time. Maybe one day we are able to create the molecule, but it's a long path. We need to start creating the molecule, measuring step by step each one of these degrees of freedom, and maybe one day we can use that as a lab, as a laboratory for nuclear and particle physics. Now, the first experiments we did around 2020. So the idea was to use CERN as a way to create this unstable nuclei. So we use a 1.4 GeV proton beam from the PSV, so one of the CERN accelerators, to collide with an uranium target. And when it collides with this uranium target, you produce a gas of many different nuclei, among them, or some of them being radium. So we inject different gases containing fluoride, such that some of the particles or some of the molecules that were going out were radium fluor plus. But there were many more contaminants. So we have to separate the masses with a magnet. And then, even though we separate the masses, that's still challenging because all of this happens in a very hot environment. Okay, we are looking for these micro electron volt scale measurements, but the nuclear reactions, so those are giga electron volts protons that are hitting this uranium. This is a very hot gas. So first we need to send it to an ion trap where we can do buffer gas cooling with a helium gas. We trap for a while, for a few milliseconds, cool down the molecule, and then once we are happy, we send the molecule into a beam line where we can interact with different lasers. And the principle of the measurement is as follows. So you do all the mass separation with a positive ion, radium fluor plus, but the molecule with the interesting symmetries is neutral. So we need to neutralize in flight. So we do that by colliding with a gas, in this case, sodium. So now you are left with radium fluor neutral. So at this point, we can send different lasers. If the lasers do not interact with the molecule, then nothing happens to the molecule. You follow a 0-degree path. But if the laser interact with the molecule, then the molecule gets excited and then ionize. And then instead of having a 0-degree path, this is going to be deflected because it's now ionized. It's going to go from neutral to plus again, and then we see a click in our detector. Okay, that's the simple principle of the experiment. Now we scan the lasers and measure the clicks on our detector. And when we see clicks, it corresponds to this transition energy that we want to measure. The challenge is that there were many unknowns when we started the experiment. So I'm going to skip all the many technical details that we have to overcome to do those experiments, and I'm going to go to the punchline, okay? So we managed to do the experiment. So it was very successful. We demonstrated that we can create the molecule, and we are able to study in 2020 the electronic degree of freedom. Okay, that was a major milestone for us. And we were very happy because this called the attention not only from the physics community, but also the chemistry community and the astrophysics community. We realized that we can these molecules can help us to study the chemistry of the heaviest elements, or there is an interest to look for those rare molecules in space. So we develop a very sensitive technique that is able to measure a molecule one by one in a very large background. Okay, so we're very excited that we can contribute, although our long-term path is many orders of magnitude away. We're very happy and motivated by those initial experiments. So now that we know how to create a molecule, we start to play the games that we like to play as a nuclear physicist, and we can add neutrons into the nucleus. Okay, so we can one by one add neutrons into the nucleus and see what happens with the molecular structure. And we were very excited to see that small changes of the nuclear size have a large impact on the molecular energy levels. And that's now, when you look back, it's kind of obvious, because that's what we wanted, right? We wanted the electron to have a good overlap with the nucleus. And that was a good demonstration and quantified effects. So how large was this overlap of the electron wave function with the nucleus? And that further motivated us. We went beyond, we did more development. So we improved the precision of the experiment. The blue line is this peak that we want to measure in 2020. So the red one is what we did in 2024. Okay, so now we're very close to the natural language. So that's mainly the limitation. It's mainly the uncertainty principle now. Okay, measuring these very narrow energy levels. And another important development is that although the molecule can have many degrees of freedom, so you can excite the molecule, and a molecule can decay to many possible levels, this particular molecule, when you excite, it prefers to come back most of the time, and in this case, 99.6% or more, back to the ground state. So it works effectively as a two-level system. And that's very unique for this molecule. Okay, there are not many molecules that behave like that. And that's very exciting for us, because it is a main requirement that we can use for laser cooling, because we can excite the molecule many times and it will prefer to come back. Most of the molecules will go to a different state. So although it's extremely complicated, it's a complex system, it effectively works as a two-level system. And that excited us even more, because now if we can do laser cooling, we can apply the advanced quantum science techniques that the community has developed. So that was done mainly with 226. Now that we can replace the neutrons, we were able to add neutrons. Now we have a nuclear spin, and we measured the magnetic interaction between my electron and the nucleus. And that was another great surprise for us. So we are very sensitive not only to the typical nuclear magnetic moment interacting with the effective magnetic field produced by the electrons, but we are also sensitive to the distribution of the nuclear magnetization, how the nuclear magnetic moment is formed. Because when the electron is inside the nucleus, it sees a different magnetic moment, right? This contribution has to be, or is fairly large for these molecules, of the order of 5%, which is great news. That's what we wanted, right? A good overlap with the nucleus, and it's allowing us to see phenomena that we, to our knowledge, was not seen before in molecules. Okay, even stable molecules. So those results were published last year, and we have done many more works. Okay, that now that we have the technology, we have applied that to measure a different molecule like tinium fluoride, and that also proving that there is also a high sensitivity to CP violation with those molecules. So this is just the start of a very ambitious experimental program. Now here's where we are, okay? So 2020, and step by step we have gone into all of these orders of magnitude. So now we are already there, okay? We are already being sensitive to nuclear phenomena, like these nuclear properties or properties of the distribution of the nuclear magnetization. So now we are already here really trying to go for this parity and CP violating interactions. So all the experiments I explained before, although I didn't go through the technical details, they were done with a molecule that was flying. So the limitation there is a fundamental limitation. So the molecule flies, so we cannot interrogate or we will need a very long beamline. So we would like to move into trapping the molecule, and especially because we can do laser cooling. So that's what we'll imagine. Going from microseconds, that is our current interaction time, to more than hundreds of milliseconds. And that's going to be the main technological development that we would like to do in the following years. Let me flash this very fast. We joined force with two different PIs, with John Doyle at Harvard and Nick Husler at Caltech, that they have been working in laser cooling of stable molecules. And Nick as well has done spectroscopy now with radioactive molecules as well. And the main idea was to join force with them and a new facility for rare isotope beams here in the US with this in mind, okay? If you give me a beaker that contains some particular nuclei, we will do all the technological developments to finally trap a molecule in a MOT, in a magneto-optical trap, okay? And the idea was to do all of this process, okay? Conceptually, it's very simple. You give me the liquid with the nucleus, and then we do all the steps to have a single trap molecule. And we were very lucky because many talented people doing the experiment. So here is a bit more of the technical details. We put the liquid on a foil. We ablate the foil with a laser. We produce many molecules. We cool down with a cryogenic gas. And then we send many lasers to the experiment that do the cooling of this molecule to finally have a trap. And then in the long term, our ambition is to have like a lattice or tweezers of different molecules. So that's a bit more of how the design looks like, the cut design. So the length, just to give an idea, is about 2 to 3 meters length. Okay, it's still what we call a tabletop experiment, although we need to use more than 2 tables, but it's a laboratory size experiment. So this is as it looks like in reality. So this is an example of the box. Basically, everything happens at the center. We ablate, we create a molecule, it goes out, and when it goes through a beam line, we send different lasers, and hopefully we'll have the laser cooling. So it's that just to give you an idea how it looks like. Okay, I don't pretend to explain all the technical parts. Our collaborator has developed those cells also to go even beyond diatomic molecules. We can do polyatomic molecules like radium-OH. So this technology is spanning fast to more and more complex molecules that they have complementary advantages. So here's where we are now. So we already tested all of this with a closed cell without opening the beamline with radium molecules. That was the work done at Caltech by our collaborator, and we will start to do this here soon. The experiment is located at Harvard, so it's a strong collaboration between the 3 institutions. We already tested the interaction with lasers using barium fluoride molecule. That is what we use to do our test, and hopefully after the summer, we will start to do the cooling of the actual radium fluoride molecule. So this is progressing fast, and it will be exciting because once we have the trap molecule, we will be very close to do a CP violation measurement with this molecule. And we estimate that more than 100 molecules to be trapped. As I said before, you might remember, if we trap a single molecule, we can already go to the state of the art. And the technology has improved so much that we have even ideas to trap more than 10 to the 5 molecules, but step by step. Okay. So let me finish with another experiment that we are doing in our lab, and there is a lot more to learn beyond CP violation. Okay, CP violation is a main simple question. It's a yes or no. Do we see a 0 or we see something different than 0? But we know very little about the P-violating nuclear interactions, okay? At the fundamental level, we know the how the weak interaction works, but once we put in a nucleus, we know very little. Okay, we don't know these electroweak currents in nuclei. So a way to measure that is if you have two states of well-defined parity. So if you don't include the weak interaction, they have well-defined parity. But once you include the weak interaction is going to mix states of different parity. Okay. So this numerator is what we want to measure. But the mixing is going to depend on the energy difference between those two states. Okay, just first order perturbation theory. Bottom line, if your energy difference is small, then you can maximize your sensitivity even to a very small effect. Okay, so in nuclei, this energy difference between states of different parity are typically in the mega electron volt scale. So it's very hard to see the effect of the weak interaction. In atoms are like electron volt scale, but in molecules, those go to micro electron volts. And actually are so close that you can apply a magnetic field and they can come closer together. For a magnetic field that is realistic at the lab level, so Teslas, okay? So effectively, you can bring your two states of different parity very close to zero. So now the enhancement is no longer 10 to the 6, but it can be more than 10 to the 11 or more than 10 to the 12. The enhancement is going to depend on how well I can bring those two states close to zero. And that's great because 10 to the 6 was an amazing amplification, but 10 to the 12 means that many experiments we thought impossible will become possible. And that's another experiment that we are trying to do in our lab. So we're trying to create a molecular ion. It's not neutral in this case. And then we are going to trap the molecule in a magnetic field. That's called a penny trap, right? And we tune the magnetic field such that we amplify the sensitivity to this particular symmetry violating term. And that's happening in our lab. So this is an experiment was a few months ago. Now it looks far more busy. But the main part is a magnetic, a superconductor magnet, and we trap a single molecule inside. And we interact with the molecule where we maximize the sensitivity to these parity violating effects. So this mainly helps you to any parity violating effect because it enhances that by orders of magnitude. It's not so good to measure CP violation because you are enhancing all of these or parity violating effects. The effect of the WC within the nucleus is going to be enhanced far larger than the CP violation. And we hope to see results in the following years. So there are many more people that have been going into this field. Okay, in the last few years, the power of these radioactive molecules has been recognized with different nuclei, different platforms. So the community is growing and doing even better job that we can do. So we have groups interested in polyatomic molecules, even more complex molecules, or other ways to study the molecules by having ultra-cold atoms that you can assemble to do an ultra-cold molecule or implanting molecules in solids, or techniques that have been pioneered with molecular ions. So there are many more methods, and it's a community that is growing very fast. And we need more people, okay? For the students that we listen to this talk, we always need more people. We need new ideas, fresh ideas. So this is just starting. There is a lot to do with these kind of technologies. Here is the cartoon. You have some fundamental physics phenomena that you want to study. We use our nuclei as a way to amplify that by changing the imbalance between neutrons and protons, or by controlling the number of neutrons or protons systematically. And once we create this amplifier, this nuclear amplifier, we can put that in a molecule. And we use the molecule to provide defective fields that will interact with these nuclear properties with an overall enhancement that, as I show, can be more than 10 to the 6. Here is where we are now. Okay, we are measuring at the 10 to the minus 9 level that I showed before. So there is a lot to do in the AMO evolution. We have seen atomic clocks at the 10 to the minus 18 level. Okay, we are very far away in the quantum evolution. And we don't feel bad about that. We actually feel very positive because there is a lot to do. So this is the tip of the iceberg. And let me close with this sentence that I introduced at the beginning, okay? When Michelson told us about, wow, our future discoveries must be looked for in the 6th place of decimals. I think that time already passed. I think now it's more like 12 place of decimals in any system, okay, in radioactive molecules. We know that once we reach this level of precision, we will access to the electroweak physics. And this will be a lab for electroweak physics and high energy physics that has a lot of potential. I hope I convince you. Okay, thank you very much.
Wow. Thank you, Ronald. This was a lovely talk and lots of new exciting things happening in this field. Thank you for sharing that. I was actually gathering some questions for myself, but you were answering them. As soon as I get the question, the next slide would answer them. I was actually, the in-flight part, it was like, that was something. Before I open the floor, if there are questions here on the call, or I'll check in to YouTube, I wanted to ask you, in your field, are there simulations playing a role? Do you guys have even like simple, I don't know, toy models that you can actually simulate in the computer and then inform your instruments?
Yeah, thank you. So that's indeed very important. And it's interesting how fast it's evolving this field. And let me see if I can maybe use this. Okay.
Inform your
We have different ways, right? When we measure an energy difference that depends on a molecular parameter and a nuclear parameter. This blue is unknown, and the red we get from molecular theory, for example, or from an independent experiment. So theory plays a role here, where we need to define that. When I started that, the theory predictions were at the 10% level of this red part, okay? The best, that was 2020. Nowadays, they can do percent precision, okay, 1% or better. So the advances on many-body physics and supercomputer power, and now we have AI boosting this. This has been incredible. And this precision of the theory means that we have this electric and magnetic field under control, so we can access very fine details of nuclear and particle physics. Now, from the quantum science point of view of how we trap the molecule, how we interact with the field, so those are many simulations. And those experiments used to be like you manually tune everything, okay? So now we are very excited because complex molecules, so many things are happening in parallel, okay? Not only supercomputers, but laser technology. When I started my PhD, you will need a room to have a single laser. So now you can buy a rack of 20 lasers, okay? So now the scale of the experiments, you can imagine doing very complex molecules and for more time. And all of these processes simulations, and these simulations that are well-known physics, like electromagnetic interactions, laser atom, it helps us to guide how we define experiments. So.
Thank you. Okay. Are there questions here in the call? Go. Yes, Carla, please.
Hello. Thanks for the talk. Very nice. I have a question. How do you measure these signals? I'm curious I know that you say I will not go to technical things, but I'm very curious how you measure these tiny signals.
Yeah, no, thank you for asking. So yeah, indeed, I didn't went to all the technical details, but so let me start with let's say the simple ways we will do it. So all that you want is the energy level distance between those two, okay? And this, imagine here is an electronic transition, is typically electron volt scale. So one proof can be you have your molecule and then you have a detector next to it, a photodetector. And then you scan with a laser in one direction, right? And if the laser is non-resonant, you don't see anything in your photodetector. But when the laser frequency is exactly the resonant frequency. You excite the molecule, and photons goes everywhere, but time to time the photons hit your detector. So that's the, let's say, the simplest fluorescent technique. And then once that happens, you write down the frequency of the laser, and that's a direct measurement of this transition energy. So that's an advantage that we have in respect to particle physics, in the sense that the system that we use to prove is the laser, which I know with extremely high precision. And we have many other methods to prove, but that's basically the base level of how we can do it.
Okay, thank you.
Any other questions here from the call? Let me see. Let me check. Oh, go ahead, Joel.
Hi. Many thanks for your talk. I really enjoyed it. It was very, very nice. I was wondering about, in one of your plots, you show the timeline and the evolution of the sensitivity, and put it and compare it to the standard model prediction, right there, the standard model contribution to the EDM. Oh, no, right, no, not the electron, the
Okay.
next one,
Yeah,
right?
super.
Yeah. So here, when you mention this standard model contribution to the EDMs, how are these calculated? What's the uncertainty in this calculation? For instance, there's now this big well, at least last year there was this debate on the strong CP problem, if it existed or didn't exist, if this could provide a contribution to the neutron EDM and things like so. So I'm wondering how is this standard model contribution calculated, because you need to have that under control in order to be able to say, okay, this is new physics.
Right. Yeah. So this is the worst case scenario. So indeed, there is a very large uncertainty in this value. Okay. So this is calculated so well, and then we put the limits of the worst uncertainty that we have. So how this is calculated? So we have to assume a source. Okay. So you calculate something like the quark chromo-EDM, okay? The chromo-EDM, and now you have to put that in a nucleon. Yeah. And now the nucleons, you have to put that in the many-body system. So luckily for this particular nuclei, so the main contributions come from CP violating nucleon-nucleon interactions. Okay. And then the many-body method part tells you what will be the effect at the nuclear level. So now this has a large uncertainty. Some people claim, so let me put, I have a plot here. So I have a plot. So this is an example. So what we measure an idea and went through the details. Okay, it's an observable that is called the shift moment, but it's a proxy of the nuclear EDM. So this spark has a p-violating interaction that we don't know well. Okay, so we can assume some constraint coming from a single source, and that will be like the quark EDM. And then the nuclear structure part, this is better under control because we can know, at least we can assign some uncertainty. So the bottom line is that they claim, or some theorists claim, that this can be constrained at a small percent. Okay, I didn't put the actual value here, but can be of the order of 20, 30%. When we do the plots over there, we assume a worst case scenarios, like orders of magnitude uncertainty in that. So if we don't see anything, if we go well beyond this line, we are safe, okay? But indeed, once we approach this point and we measure something, that's going to be an interesting question. So we'll love to have this question, to see something and say, okay, is this coming from my standard model contribution or not, okay? But this line is the worst case scenario with orders of magnitude uncertainty in the source of CP violation.
I see.
But
Thank you.
but totally right. So I think the theory, more precise we measure, more important is going to be to quantify these uncertainties. Yeah.
Do you have a measure of the most optimistic scenario for the standard model contribution, where we know that there was where we know there would be a controversy regarding the
I
measure?
think this line represents the most optimistic. So
Oh,
this
that's
was,
the most optimistic.
yeah.
I thought that was the most pessimistic.
Yeah, no, that's the most pessimistic in the sense that the larger contribution that we can quote. Yeah.
I see. I
Yeah.
see.
It can be smaller than that, but the plot seems to be, and yeah, so yeah, I think we can, going into the other side, we don't know well, but at least it's orders of magnitude. To be honest, the community is not really at the point that they can assign really realistic uncertainties. Okay, most of what we have seen is order of magnitude. But there is a lot of work and there is a large community going on in calculating that with realistic uncertainties. And at this point, we say, okay, we are so many orders of magnitude away that now if we see if we see a non-zero,
Then
it's likely to be new physics.
okay.
But we need to know that once we improve the experiment. So that.
Very nice.
Great.
Thank you. Thank you very much.
Okay, we're past the hours unless there is another pressing question. I don't see anything on the YouTube or the other channels, and I hear any other question. I actually might ask just one real quick. So just for this magnify, or the way like you are seeing these experiments, I go from something that is fundamental to now I'm scaling this. Maybe to me, it's not clear at the moment why the universe will behave in the same way this molecules is behaving, on the same like the system is being built and then you are constructing it to do this particular behavior. Is there an expectation why then definitely, let's say from a cosmological perspective at the beginning of the universe, this CP violation for the matter and antimatter would actually be something that we are seeing. Maybe that just yeah.
I see. So let me see if I understand the question. So to explain this matter-antimatter asymmetry, we need some breaking of the symmetries of the law of physics, in particular CP violation.
Yes.
And beyond what we have seen today. So now the CP violation, one source, and indeed it can be a different aspect of nature.
Yes.
But at least one possible consequence is that this CP violation or this comes from a new heavy particle, okay? And this new heavy particle interacts with my system and induces this dipole-like structure. So that's basically the assumption that is done. Or you can say the other way around.
Yeah.
If we don't include that, we will not see a dipole moment. So you really need to include this new source. Okay. And it can come from this new heavy particle. That can be a source. But it can be that there is a violation of CP in the strong force. Mm-hmm. That's another source. It doesn't require the existence of this new heavy particle, but can be the strong force, this theta QCD. That is also an interesting question.
Wonderful. Okay, thank you. And I think I'm gonna say here publicly, we're gonna invite you in a few years to keep us updated with the new results. And we are very excited about all of this. Thank you. And thank you everyone. Stay tuned. This was, I forgot which number. This is webinar 198. We will have a very special one for the 200th. Of course, the 199 coming in 2 weeks is also very exciting, but there will also be a celebration for the 200. So stay tuned for this. And thank you everyone. Thank you, Ronald, once again.
Yeah, super. Thank you for the invitation. Happy to be with you guys.
Okay. And we're not live. Gracias, Ronald. Esto está fuera de mi área, pero estaba fascinante.